Hello everyone. Today we're going to wrap up our discussion of gas laws by talking about Avogadro's law, Dalton's law, and Graham's law. Previously, we have learned 5 different gas laws: Boyle's law, which relates pressure and volume, Charles's law, Gay-Lussac's law, the combined gas law, and the ideal gas law. Avogadro's law is about the relationship between the amount of particles, or moles, that are present and the volume that a gas will occupy. The formula for this is that the volume is proportional to the number of moles. The volume and the moles have a direct relationship. Basically, if there are more particles, then they need more space, so there needs to be more volume. This also means that if, for any reason, the volume is not able to change, then one of the other variables, either pressure or temperature, will have to accommodate that change. For example, think of what happens when you place Coke and Mentos into a capped bottle together. As the Mentos reacts with the Coke, a gas forms. And as the gas forms, eventually the bottle will explode and the cap burst off of it because the pressure grew to such an extent that the bottle would break. Dalton's law of partial pressures states that when a gas is present as part of a mixture, the pressure due to that individual gas is proportional to how much of the mixture's particles belong to that gas. The expression for this is that the pressure of an individual gas is proportional to the number of moles of that gas present out of the total number of moles times the total pressure of the system. So basically, the pressure of an individual gas is a certain percentage of the total pressure. The molar ratio for gas is sometimes simply written as capital X sub gas, rather than in the form that is shown here, in order to simplify it, just so you are aware. This also implies that since the pressures of the individual gases are pieces of the total, that if you knew the individual pressures of the gases, you could add them up to get the total. So this alternative expression of Dalton's law would be written as the total pressure equals P1 plus P2 plus etc. all the way out until you've added all the pressures from the gases present in the system. This application of Dalton's law is the one that is more commonly used, and so we will be mostly working with this. Our third and final law is Graham's law of effusion. Graham's law is about the relationship between the average speed of a particle and its mass. This is done by comparing the average speeds for 2 different gases that are at the same temperature. You'll remember, one of the 5 tenets of kinetic molecular theory is that at the same temperature, gases have the same average kinetic energy. Effusion is the process of a gas escaping through a small hole in a container. It is related to diffusion, but is technically separate from it. Diffusion is a general movement or spread of particles that is due to the random motion and the nature of our universe. So while it is related to the similar idea, and technically the idea of something diffusing at a certain speed is the same as the effusion rate usually, we're generally specifically going to be talking about effusion for this law. The formula for Graham's law of effusion is the square root of the mass of gas A divided by the mass of gas B is equal to the velocity or speed of gas B over the speed of gas A, where the capital M is the molar mass and V is either speed or velocity. Please note that this is supposed to be the average speed or velocity. Remember, there are always particles who are outliers, both those who are much faster than the average and those who are much slower. So we'll focus specifically on the average. You'll also notice that the position of the gases is flipped. Gas A is in the numerator on the side with the molar masses, but it's in the denominator on the side that has the speeds. Let's look at an example of how to do a calculation involving Graham's law. Determine the relative rate of effusion for samples of nitrogen gas and argon gas. When we say the relative rate of effusion, we're looking for the ratio of V of one gas over V of the other gas. So we actually just have to plug in 2 things and just get that ratio. We have to be careful about how we plug them in. So I've decided I want the smaller gas to be on top in the ratio, because then I'll have it written as the smaller gas is a certain number of times faster than the bigger gas. So I'm going to set up the velocity side as the speed of nitrogen gas divided by the speed of argon gas is equal to the square root of the molar mass of argon divided by the molar mass of nitrogen. So the molar masses for argon and nitrogen can be located on the periodic table with a little bit of multiplication for nitrogen since there are 2 nitrogen atoms present. If we plug in these molar masses, we get that the relative rate of effusion for nitrogen and argon is the square root of 49.95 grams per mole divided by 28.02 grams per mole. So our relative rate of effusion is 1.19. That is a random number that doesn't have any units attached to it because relative rates usually don't have any units. They're considered arbitrary. So let us take a look at how we would write a sentence to sum up this result. We would say that nitrogen, the one in the numerator for the rate of effusion, moves at 1.19 times faster than argon. Let's look at a second example. Neon moves at 1.87 times faster than some unknown gas. Determine the molar mass of this unknown gas. We're again going to use Graham's law of effusion, but this time we know the relative rate, so we know the V of B over V of A. What we're looking for is one of the molar masses. The way that this was worded, we know the speed of neon versus the unknown. So we're going to write Graham's law as the V of neon divided by the V of our unknown, let's just call it X, is equal to the square root of the mass of X divided by the molar mass of neon. So let's plug in what we know. We know the rate of effusion is 1.87, so our left-hand side of the equation becomes 1.87. It is equal to the square root of the molar mass of X that we're trying to solve for divided by the molar mass of neon, which is 20.18 grams per mole. And now we have to solve this. In order to remove the square root, we must square both sides. The opposite of a square root is to square something. So to get rid of the square root, we now have 1.87 squared is equal to the molar mass of X divided by 20.18 grams per mole. We then finish solving it from here and learn that the molar mass of the unknown gas is 70.57 grams per mole. A follow-up question for this could list some identities of gases and ask you to select which one it could be, in which case you would look for a gas that has a similar molar mass. For example, chlorine gas, Cl2, has a mass that's very close to this. So if that had been one of the options, that could be the identity. However, there are other gases it could also be. It'll depend on the options you are provided. All right, time to do some practice. Good luck, everyone.